Here each fn contains only irrational numbers, and hence it contains no non-empty open intervals, because any interval will contain the combination of rational and irrational numbers. So completely rationals or completely irrational numbers, these irrational numbers cannot be found in a continuously like this. So it has so each fn contains only irrational numbers. So in between them there will be rational numbers. So there cannot be any open interval fully containing only irrational numbers. So that's why each fn contains no non-empty open intervals which are fully irrational numbers. So there will be some holes. That holes are rational numbers. Something like this. Suppose this is a open interval. There will be like this. So in between there are irrational numbers. So how can we say it will be fully inside fn? So each fn is closed and contains only irrational numbers, and hence f contains no non-empty open intervals. So it contains no non-empty open intervals. Thus each fn is closed and nowhere dense. There is a definition of nowhere dense. Nowhere dense. The set is said to be nowhere dense if it contains no open interval. So each fn is closed and nowhere dense in R. So which implies that Q dash is of first category. This is the definition of first category, where each en is nowhere dense. So but already we proved that, which is a contradiction. Because Q dash is of second category. Already we proved it. Set of all rational numbers is of second category. Therefore our assumption is wrong. What is that? Set of all irrational number is of f sigma type. Here this is wrong. Our assumption is wrong. That's why we are getting contradiction. Therefore the set of all irrational numbers is not of type f sigma. Hence the proof. Here it contains no non-empty open intervals. One more way we can explain is the set of all rational numbers Q is dense. Already we proved it. The meaning is, suppose this is set of all real numbers. Suppose this is rationals and this is irrationals. Q is dense. That meaning is the things with the limit points, that is the Q dash, the closure of the Q will be equal to R. That is, the set of all limit points is, that is the closure will be equal to R. So all the limit points are in Q dash. So whenever you take a sequence, same thing for Q dash. Q dash is also dense enough, and the limit points of Q dash will be in Q. The meaning is every sequence will have a limit in Q. Similarly here, every sequence of rational numbers will have a limit in Q dash. So you cannot split them. So we cannot find a continuous open interval which is completely in Q or Q dash. So like this also you can think. So now the last result. The last result of unit 5. There is no real valued function. There is no real valued function f on R which is continuous at each rational but discontinuous at each irrational number. So there exists no function of this type which is continuous at each point of rational but discontinuous at each point of irrational. To prove this, we are going to assume the contrary. Suppose there exists a function, suppose there exists a function f on R such that the function f is continuous at each rational point and discontinuous at each irrational point. Suppose we assume the contrary. Now let D be the set of all irrational points in R1. Be the set of all irrational points in R1. Suppose the function is like this. Function f is defined on R. A real valued function. R. F is a function from R to R, and we know already that this is rationals and this is irrational. So suppose f, what we consider here is f is a point which is continuous at each point of rational numbers. Whenever a rational number is there, suppose a is a rational number. So whenever x approaches a, here f of x approaches f of a. That is f is continuous at the point a. And at each point of irrational number, suppose b is a irrational number. So when any number comes very close to b, f of x does not approach f of b. That is, function is not continuous at every point in the irrational number. So like this one function we assume. So like this is possible. We are assuming. So what is this? D is the set of all irrational points in R. Set of all irrational points in R. Then D contains all points of discontinuity of f, because just now we assume, no, whatever point we take in q dash, here q dash we assume it as d, let d, or you can take q dash also to avoid the confusion. But q dash be the set of all irrational points in R, then this Q dash contains only points of discontinuity where the function is not continuous. So we say that. So therefore, so now what you can tell about Q dash? So already we proved one theorem. That theorem I am going to write it here. I name this the horizontal star, that is, let f is a function from R to R, and let D be the set of points in R, at which f is not continuous. F is not continuous. That is, suppose D is a set of all points of discontinuity points of the function. Then we have already proved that D is of F sigma type set. Already proved it. Therefore, here Q dash is a set of all points of discontinuity of the function f, which implies by star Q dash is a F sigma set. Q dash is what? F sigma set. Which is a contradiction. Why it is a contradiction? You are getting a contradiction. Since why we are getting contradiction? Because we have already proved, since Q dash is not a F sigma set, since Q dash is not a F sigma set, therefore our assumption is wrong. Therefore there exists no function f on R which is continuous at each rational number and discontinuous at each irrational number. Hence the proof. And this completes the topic discontinuous function on R, the last topic of our study. So here this Q dash is a F sigma set, we are getting it because that is by this result. But this is not F sigma. Q dash is not F sigma. Set of all irrational number is not F sigma. We already proved it. You can cite that one also. We know that. Okay. So that's why we are getting a contradiction. So this completes it.